Yeah. We have stacks for I use Discord.
Actually, there is. Well, I don't know if it's dynamic, but remember last year they had them for physics, chemistry, engineering.
No.
everything.
Oh. Oh, wow. I think that was cool. I don't know how to use Discord.
It was nice. Like there's some guys that know their stuff, maybe tutors, and you can create something there and they would help you out, give you some ideas on how to work out the problem.
It's like you're stuck on a.
Yeah. Yeah, they would help you out with physics. Because physics, calculus, chemistry. Oh shit, this is the last one.
All right, let's have a look at this. So we're looking at something now, which is just a short jump from what we did with power or what we did with work and energy. And work is distinct from power in this way. So let's think about this for a second. Let's see, what was work again? Work was, we called work a force times a distance. We said that makes sense because if I'm lifting something, how far I lift it should count, right? It should count for something. I can't just say I lifted 100 pounds. It should count that I lifted it way further than somebody else. So somebody invents the concept of work. Nothing magic about that. It's just saying, well, a force and a distance would make a difference. And so power is kind of the same thing, except it is a force times time. And let's think about that. That also kind of makes sense, doesn't it? It doesn't make sense that somebody would say, well, yeah, one person lifted that weight that was 100 pounds over up in the 9 feet high, and another person did it too, but one person did it in 15 seconds and one person took 2 minutes. So, you know, would there be some way to kind of give somebody credit for doing their job faster than somebody else? Again, I just want you to have a sense of like, yeah, that kind of makes sense. It makes sense that somebody would create that. You know, why would you call one work and one power? Who cares? Those are just kind of made up terms. But the idea that somebody could get something done faster than somebody else, I mean, I find myself going, oh, you were powerful. I mean, that kind of makes sense. Oh, you worked really hard. You worked harder than that other person did. I mean, these ideas make some sense logically. I can see why somebody would want to invent that. And so, for instance, I'm riding my mountain bike. Between me and my bike, I weigh 210 pounds. I climb 1,800 feet in elevation, and it takes me 42 minutes to do that. And that wouldn't be the same as somebody else, right? Like they might do it faster than me. And so we might say, oh, you're more powerful. And so the only thing that might change between me and somebody else is time, or maybe I would, even myself would go a few days later and do it faster. So I'm more powerful. And so, you know, that scenario right below power there kind of represents what it would take. Notice the first part of this, I guess you would just say is work, isn't it? Like, isn't that a force of 210 pounds? I should add pounds to that, I suppose. A force of 210 pounds elevated 1,800 feet. Woo, that was a lot of work. But if somebody did it faster than somebody else, adding time in, that's interesting too. And so wait, I guess is that, let's think about that for a second. Well, let's look at power down here. If power is a force times the time, what would the units be for that? Maybe let's think about it in metric first. Yeah, let's see, force is newtons and time is in seconds. So that'd be Newton seconds. Yeah, and you might be familiar with the term horsepower because we're going to get to that in just a second. But the idea that cars have different horsepowers and motors have different horsepowers. I mean, that's how we measure things. We don't say power, we say horsepower. And of course, that is exactly what it sounds like. Back in the day, if you wanted to, you know, lift something heavy, you had a horse do it, right? You had a horse drag something through. And then, you know, eventually somebody invents tractors. It's like that tractor will do the work of 12 horses, you know? So then it's like, oh, that's a 12 horsepower tractor. I mean, it literally started as simple as that. And of course, as technology increased, somebody said, well, we got to kind of put numbers to this because obviously all horses aren't the same. And, how are we gonna work that out? This horse is an awesome horse, but it's, 20 years old, kind of worn out. It's like, we got to somehow put some numbers to this at some point. Well, this is going to, close the gap in your mind a little bit. You probably have, some things in your mind in that regard. I'll show you some things in a second too, but let's see, that would be Newton seconds. Okay, that makes sense. But then a Newton is a kilogram meter per second squared, right? So that's also true, is it not? All right. Kilogram meter per second squared, that's what a Newton is. And then times seconds, because it's Newton seconds. So then I guess one of those seconds would cancel, wouldn't it? So then it'd be kilogram meters per second. Wow, that's embarrassing. I just lied to you. Should have looked at my notes. We got to fix something here. It's not a force times at time. It's a force times a velocity. Sorry. Sheesh, that's a huge oversight. And that's in your note. You said this is in your note sheet. So it's the same idea. What I said before is not untrue. In other words, if somebody has a certain force, but then kind of how fast do you do it? It's not just kind of how much time it takes. It's like how quickly can you do that in terms of a speed? So if this is force times the velocity, velocity is measured in meters per second. Sorry about that. Geez, that's a massive stupidity. And just to simplify this, I think I'll stop this more complicated approach. So it's really newtons times meters per second. But the other day, didn't we say work was a force times a distance? Well, wasn't force measured in newtons and distance measured in meters? So in a sense, this is like Newton meters per second, or I guess you could say this is work divided by time. That's kind of why I got screwed up with the time thing. So it is work with respect to time. Like I was saying conceptually before, if you get your work done in less time than somebody else, then you're more powerful, all right? So really, in a sense, this is kind of its practical definition, force times the velocity, but it can also be thought of as work divided by time. So if I put all those units together, a force times the distance divided by time, that's kind of what it's adding. It's actually taking work and saying, "Ooh, you lifted that weight, that 100-pound weight, and you lifted it 9 feet. Nice job. But how fast did you do it?" So you're adding time to what was already there. Does that make sense? That was a lot of work to lift that weight that distance. And now we're saying, well, how much time did it take? Divided by, was that 9 minutes? Was that 12 minutes? And notice a small time, some kind of a work divided by 9 minutes. And then somebody else says, I divided it in 8 minutes. Does it make sense? Dividing by a smaller number makes this more powerful. This person's more powerful. Dividing by a smaller number makes this bigger. So the power number will get bigger if your time is actually less. So do you see why the time ended up on the bottom? That logically, that kind of makes sense why it would be the case. So we're adding to the concept of work and saying, well, let's throw time in the mix then. So in a sense, you could say maybe even power is, and you don't need this, you need your note sheet, but just the concept that power is equal to work, which is a force and a distance divided by time. So So Newton meters per second. Yeah, that makes sense. Work divided by time. Sweet. So the fact that I did a certain amount of work, 210 pounds, and I lifted it 1,800 feet in the air, and that's a fairly common mountain bike ride right there. I lifted it 1,800 feet in the air, and then I say it took 42 minutes. Does it make sense? I could actually divide all that out now. I could sort of follow that formula and come up with a power number for me for my particular ride based on my weight and how far I rode and how much time it took me. Let's see. Well, what would this all look like in our system? Because notice my example wasn't in metric. So of course we could convert my weight and distances to metric and so forth. But what would that look like? What would this look like in the standard system? Well, what was force? Force was pounds, right? So in our system, I guess that would be pounds. Distance was feet, so foot pounds. Oh yeah, that was work, foot pounds, right? That makes sense. And then time was typically in seconds. And so yeah, it really hasn't changed much. Newton meters per second, foot pounds per second. Okay, that kind of makes sense. Yeah, like, well, in a sense, torque has got to rotate around and up. So you're right. I mean, it's a good observation. Remember how torque was a length times a distance, but that had to be rotating around something in order to call it torque. It caused rotation. If I'm just lifting something 1,800 feet in the air, it's the same exact unit, but it's not torque because I'm not trying to get something to go around in a circle.
Torque would be work though.
You can look at it that way. It's exactly right, which is of course interesting in the case of a bike because you're actually pushing on a pedal that's a certain distance away from the crank. And so, you know, it's your force on your leg times that distance, which actually kind of determines how much torque there is. So.
But I'm just thinking in terms of like cars, like car has 200 horsepower, 400 pound-foot of torque,
Right.
which is a force times the distance.
Yeah, and see what I don't know, maybe you do, is what is that torque referring to? Because the motor turning would create a certain amount of torque that just kind of comes out of the shaft, and it's that with gears and so forth that you turn into wheels moving. But you know, it's a function of the distance, and so if it's this tiny little shaft, that's one sort of rotation.
Like the difference between horsepower and torque is from a stop, and then horsepower is once the object is already in motion. So the difference in power between the two that you could accelerate.
Yeah, and as a quick example, I think I mentioned this in other classes before, but I bought my dream car, the '66 Fastback Mustang.
Okay, yeah.
And it is 289 horsepower, which is actually, that's not wrong. That's the cubic inches. It's backwards. Anybody know Motors Enough? What the heck does that refer to? That's a volume. Like, what are we talking about here?
Oh, for displacement.
That's the volume of the cylinders. Now there's 8 of them. So if you take that number divided by 8, that would be the volume of one cylinder. So you put, you know, a gas air mixture in there, you light it on fire. Basically, the bigger that is, the bigger explosion, the harder it's going to push. So in the end, that is literally an expression of the cubic inches of the cylinders that you have to work with.
Engine is like a 5.0. That's the displacement of it, right? Does that translate to the horsepower?
Yes. And that 5, they go together. In other words, a bigger cylinder, bigger explosion, that's going to cause, you know, it's going to be more horses effectively. And the 5 is liters. So there's also metric. And so this is an older car and it's an American car. So it's measuring cubic inches.
All clear. The building can resume normal operation. All clear, all clear. The building can resume normal operation.
Okay, guys, it's time to be normal now. We haven't been being
All
normal.
clear, all clear.
Please, no more. So that's kind of a cool number. So that's a reference. A bigger number there means a bigger car. Now, in this case, that actually translates to 164 horsepower. Now, in terms of cars and racing cars, that's nothing. But if you think it used to take 164 horses to do what this car is doing, that is a crazy invention. You know, it's amazing. So of course, you know, what is a horsepower? Well, this is in your note sheets, and I just have to write this down. But 1 horsepower, 1 horse. Remember I said before, it's like a horse is not a very technical definition for how strong something is, because horses are all different. 1 horsepower is 550 foot-pounds per second.
Well, on top we have pounds per foot, doesn't matter.
What do we have?
Times speed and then the bottom speed times pounds. Doesn't matter which one goes first. Where you.
Oh, got it. Yeah, pound feet versus feet pound. No, they're multiplied. So a lot of times you say it is foot pounds. So that's why I kind of turned it around. But no, it doesn't matter because it's just 2 numbers being multiplied. Now, again, can you picture that happening? Like somebody said, all right, let's just get, you know, like an average horse and let's have it pull something. Let's have it pull something, a number of pounds, a number of feet, say how long time it takes. And they're like, oh, that's about 550 if we kind of multiply all that together. So we'll just call that 1 horse. And so 550 is really random. And again, it's kind of the materials testing concept. You know, how strong is this piece of steel? I don't know. Let's pull on it and see what happens to it. And then that'll be our number for it from now on. And so this is a very arbitrary kind of a number. Does that make sense? But now that we have an actual kind of a defined number for how to connect horses to power and so forth, or, you know, these literal measurements of work and time, now we just kind of have something to work with. And so in the end, it's kind of irrelevant. It's just kind of like, well, if my car is 164 and yours is 180, yours is better, right? So it's kind of more of a relative term. Interestingly, that happens a lot. Like we have all these gauges on rivers that we run. I'm going to go run that. Speaking of power, I'm going to go run that one today that I was telling you have to carry your boat out of the canyon. I'm going to do that today. So I'll be thinking about power, trying to get my mind off the pain that I'm in crawling out of that thing. But in the end, that river, if it's running 400 CFS, we just know that's good. But what it's actually running down where we're at is different. So we just kind of know, oh yeah, back up at the gauge way upstream. As long as that number is kind of in here, then where we are, it's gonna be great. Yeah, dry suit actually, even better.
You go down the avenue before.
No, just below that. I got friends that have run sections of that. It's a good place to die in there. Yeah, we start right where the falls comes in downstream, hike down that cliff, and then take off from there. Awesome. Oh, can't wait. Let's see. So that's one conversion, and then so that's kind of our conversion. But it turns out that the metric version of this is a watt. 1 watt is 1 Newton meter per second. Notice they made it a little easier. They didn't just say, oh, 1 foot-pound per second is 1 horsepower. And you can see why, because it was related to horses. But they just said, okay, well, let's just rename. Again, this is one of those things where Newton meters per second, what a ridiculous unit that is. So let's just call them watts. Watt was just invented to replace that. Does that make sense? So you got to see that one as a renaming, whereas kind of our system was not. Our system was not just a renaming. Because we threw a 550 in there. And then of course, like what if you wanted to convert between sort of the metric world and our world? Well, there's a conversion for that too. And of course, you could make this up for yourself. Does it make sense? You could convert Newton meters per second into foot-pounds per second and actually get this yourself. But you'd have to know how many feet are in a, let's see, is it right? Yeah, how many feet are in a meter and how many newtons are in a pound and kind of make that conversion yourself. Well, somebody's already done it. It's 1 horsepower is 746 watts. So when power is talked about, the answer will always be horsepower. It'll never be foot-pounds per second. And therefore the 550 is going to get involved for these kinds of problems. Okay, well, that was fun. Why don't we try that now? Let's figure out how much horsepower. My example up there earlier, I went 210 pounds. I carried that between my bike and my own weight. I carried it 1,800 feet. Notice I said elevation gain straight up. I didn't actually pedal straight up. I pedaled at an angle, but the end result was I was working against gravity, which remember is only going down. So although I might have ridden 50 miles, all that matters is I went up 1,800 feet. Doesn't matter how far I pedaled, it matters how much up in the air I went. So, you know, based on the units there, well, everything is already the right units, 210 pounds, 1,800 feet, well, except for 42 minutes. So does it make sense? I could say, oh, I know what my power was. That's not hard. My power would be 210 pounds times 1,800 feet. And then 42 minutes. Are you doing this in your chemistry classes? There are 60 in 60 seconds. There is 1 minute. That way the minutes cancel. And so that's how you kind of get yourself to go, oh, that's right, I multiply by 60. Maybe you don't always need the units because in your case, you're a lot more familiar with seconds and minutes than you are with units and moles and milliliters and all that kind of nonsense that's in chemistry. But it's like, that's going to get me foot-pounds per second, right? So if I punch that, let's see, I already write this down, I get, guess I didn't. It is, but I can't see where I wrote it down. Oh yeah, I did 150. And so that's a true statement. That's how powerful I was. It took me 42 minutes to do that job. So I only had 150. But again, we don't speak about power with those units. We speak about it in horsepower. So this is where it'll be interesting because you probably can guess I'm not as powerful as a horse, right? Horses are stronger than me. So, am I going to be as powerful as a horse here? My guess is no. Well, again, let the units do the thinking for you. If I have 150 foot-pounds per second as my unit, then don't I need to multiply that by something with foot-pounds per second on the bottom and horsepower on the top? Like, isn't that what I have to multiply by? So that this unit will cancel with that unit. And so I need to know how many horsepower is in a foot-pound per second or other way around. Oh, yeah, 1 horsepower is 550 foot-pounds per second. Oh, I got to divide 150 by 550 now. That's going to be my horsepower. Punch that, I get 0.273. Dang, disappointing. Has anything changed here? No. I've just changed it to a unit we're all familiar with, just like PSI, pounds per square inch, is how you measure pressure in our system. And so this kind of tells me, oh yeah, you're about 1/4 of a horse. That actually kind of sounds about right, doesn't it? Maybe even a little too high. So the fact that I jump in my car, which is so much larger than that, that's why it's so much nicer to go up the hill in a car. Now, just for the heck of it, let's see, it already have these loaded in. I do not know. Wow, I got a lot of crap in here. I don't have a lot of these with me, but I just brought a few of them. So I went online and these are just places I've seen horsepower. So I'm always doing construction work. So, here's the incinerator garbage disposal. So it's like, what's this one right here? Notice 3/4 horsepower. So that's disappointing. It's stronger than me, right? It's 0.75 horsepower. That was only 0.27. But again, those are measurements of when you stick stuff down there, is it going to, kick butt on it, or is it going to get worked over? Notice this one's 1 1/3. That's quite a bit bigger. So it's like you see this stuff around a lot. You're probably thinking of it in terms of cars, but all motors have a horsepower associated with them. Table saws. Is this all of these, or did I have other stuff on it? Yeah, I did, table saws. So check out this table saw right here. Bam, 3 horsepower.
Is that 3 horsepower? Boat? Still aluminum boat.
Yeah, that's right. Little outboard motor on my old sailboat was 9.9 horsepower. So it was like 3 table saws, right? So you see what I'm saying? Like this stuff is kind of everywhere. In the end, you know, it's not like you have to totally understand it. It's like, oh, look, that one's 5 and that one's 3. Guess which one's going to cost more? You know, it's the same exact one. It just has a more powerful saw in it. This ad that I found online is outdated, so I'm sure this isn't accurate anymore. But yeah, it costs you another $300 to get the better motor in that one. And obviously, in this case, the work it's doing is chopping through wood. And the question is, how quickly do you want it to chop? You see what I'm saying? It's like work and time. And here's these little wimpy ones. 1.75 horse. Check this out. So these are the awesome cars. Like this is not your car. Notice this is 4 times. This is 4 times as powerful as my, you know, what used to be a really cool car. Not a race car, but, and that was a stripped down, that was a family version. I mean, they had faster versions for race cars and stuff like that, but it's like, these are the high-end ones. Wow, you know. But that's kind of rad. I don't know a ton about cars, but again, do you have to know anything about them just to compare this random number, even if you don't understand it? No, if yours is bigger than someone else's, it's going to go faster. It's not that complicated, but it actually does work its way down, which is of course the job of an engineer. Somebody who is designing cars would actually need to think about, you know, what size pistons do I want and how much cubic inches that is that. And then I would, and of course, that explosion has to get converted through a lot of processes inside the car, right? Got the little pumpkin joint in the back that translates the rotational motion heading toward the back into rotational motion going this way for the tires in the back. Does it make sense? There's an efficiency loss there, friction and all that stuff. And so that's what I want to say something about now. So this is also in your note sheet, but efficiency, you never get the full efficiency. Is my bike fully efficient? Nope, you got a chain, friction. Bikes are pretty good though. There's not that much stuff there. The more stuff you get, the more moving parts you get, kind of the worse it gets. And you can probably appreciate, you know, like the power that's in gasoline when you explode it. You know, there's friction of the cylinder sliding along inside, or the piston sliding on inside the cylinder. It's like there's a lot of loss inside a car, and we'll do that example in just a second. But for those of you taking strength of materials, I apologize, but it's epsilon in your book, which is the same as strain, which is as if it isn't hard enough to keep all this stuff straight. And basically, this is just basically power out divided by power in. Now, what's going to be bigger of those two numbers? Power out or power in? I put power into my bike and then I roll up the hill. Power in is always going to be bigger than what you get out. If I put power, if I pedal in the bicycle, I'm putting power into the pedals. Am I going to get all of that back out? No, I'm not. So therefore, this is always going to be less than 1. It's a percentage. And that's actually kind of good. And notice, you don't have to divide it this way. But the idea is if this number, if this efficiency number was like 90%, then basically that means you're getting 90% of whatever you put into it actually into the tires, rolling you down the road. If it was 65%, like a car might be, then whoa, I'm losing 35%. You know, the energy I had to put into this because of all this friction and stuff, I'm losing a lot of it. So power out is always smaller. You're always getting less out of something than you put into it.
That's weird, because I would have thought that like the drivetrain on a mountain bike would try to power it out. But
Well, you're thinking gears.
yeah,
And that's true. Like, but nothing is gained there. In other words, if I put it in a higher gear, then I can actually hunk my meat up the hill in places I wouldn't be strong enough. Like I don't have enough horses to pedal up the hill if it wasn't geared correctly. But you don't gain anything from that because now I have to spin the pedals way faster to make that happen. And so, yeah, so you're thinking of kind of two things at once. Yeah, basically makes it possible for, you know, what I have to work with my leg muscles to actually still get me up the hill. So that's kind of interesting. Oh, okay. So what does that mean to me? So let's say my bike is, I'm making this up, I have no idea, 80% efficient. Extra credit, go look into that. Can you find online? This could be a quick Google search. Can I find online like how efficient is a bike in general, just roughly? All bikes would be different, but you know, is 80% a reasonable number? Can't remember. Did I look that up and put a real number there, or did I just make it up from random?
Well, the car's like 20 and then
So-
the formula's 50.
Yeah, so you know, all machines would be kind of different. And of course, your goal as an engineer would be to try to design stuff that could be as efficient as possible. Okay, so all right, what does that mean for me? Okay, great. Well, I got my equation there. E equals epsilon equals power out over power in. So I put 0.8 over there, and now I'm stuck. What's the 0.273? Is that out or in? And there's a right answer to this, but you got to think about it to think about what it would be. So would you agree this is what happened? That's what happened right there. I had that weight, I had that distance, and it took that time. That's actually the bike going up the hill. That's power out. That's not me pedaling, because that's actually what happened. You see what I'm saying? So that's actually the power out. So if a car moves up a hill, that's it moving down the road. That's actually the power that you got, but you had to put more power into the engine to get that because it isn't perfectly efficient. Nothing is. And so, you know, what did I have to do to the bike? So actually that wasn't my horsepower, was it? Actually, as it turns out, that was the power that the bike went up the hill. So what did I have to do with my legs to get that to happen? Well, if you punch that and solve it, you get so sweet. I'm a third of a horse now. I'm actually a third of a horse, not a quarter. I'm doing a little better.
This is kind of related to the same what we did on Tuesday, where your distance here is your Y distance,
Mhm.
your 1,800 feet, because your X would have kind of been, you know, been a wave almost.
Yeah, and that's correct. But again, that's all unrealistic because we're saying it's without friction. Well, is there friction as I'm pedaling up the road? Does it matter that it took me 9 miles to get that high? It actually will. That'll make me more tired. And so in the real world, you actually would have to consider how far it was horizontally too, and then think of that as a force of friction pushing against you. And again, hopefully that's nice and smooth. You got good bearings on your wheels and all that kind of stuff so that it was kind of minimized. But yeah, this is again, kind of, we're thinking of this without friction. Therefore, all we have to care about is straight up. And we say straight up just because gravity is going straight down, it makes it really kind of easy. But we would realistically have other forces that were working against us at an angle, and we'd have to calc those in if we, you know, wanted to get it perfect. Okay, well, that's cool. Let's just try an example. Whew, 2 classes. This is hurting me. And notes section I did 14.44. Okay, so let's consider this. Stare at that for a second. This is part of what I gave you the other day, right? That we ran out of time for, or did I not give you this? I don't think I did give you this actually. Yeah, I don't think I did give you this. I have it with me. So kind of be looking at, yeah, strength of materials.
Yeah.
So, here, just a second. And also be looking at your note sheet, just so that you kind of. Works. Okay, so I got this car, it has a certain weight. Notice it's in megagrams. That's kind of a crazy number. Remember, that's not a force. Since it's metric, we got to make it a force. So that's something to think about. And so I'm taking it up this 7-degree slope at a constant speed. What does it mean when it says constant speed? Acceleration is 0, and it's traveling 100 kilometers an hour. And if you're like me, you don't have a super good sense of how fast that is. And notice, and I like this, it says mechanical friction and wind resistance are neglected. I wish it had said negligible. They exist, but they're kind of small. So determine the power developed by the engine. That's power input by the engine. If the automobile has a pretty poor efficiency of 65%, so we're losing 35% of the energy as it kind of goes from gasoline to motion in that whole process. So this is really similar in the sense that it's like a car going up a hill. So first of all, let's see, 2 megagrams. That's 2 mega. Mega, that's 1,000, right? Gigas not 9 zeros, so mega is 6 zeros, right? You all agree with that? So it's actually 2 million grams. But why am I writing it like this? Because of newtons. If I take that times 9.81 meters per second squared, notice I have kilogram meters per second squared. So its weight, if you will, not its mass, its weight would be those multiplied together, which is 19,620 newtons. So that's the car's weight. And again, that's like a lot of weight to horse up the hill, right? I only had to carry 210 pounds up the hill. This is 19,000 newtons up the hill. That's a lot of weight. But remember, that's going straight down, right? So I think I'll be lazy over here and say, all right, cool, that's straight down. And so I've got to convert to this new axis, and I would like to do this. What's that?
Because technically all that weight is on the wheels.
Yeah, that's exactly right. So this is, I can think of this as a particle pushing into the ground just because they said there's not friction that I have to worry about. So I can just think of it as a box sliding up the hill without friction. So I don't have to split this between 4 different wheels. I can just think of it as the weight of the car and kind of put it wherever I want to. But you're exactly right. There's no weight where I just drew it, right? It'd be on the wheels. So notice I'm creating an axis for myself that is in the direction the car is traveling. So I'm rotating that. But unfortunately, 19,620 is not in that world, all right? So we saw in the last sections that you have to convert it to a curved world, normal and tangential if it's curved. If it's straight like this is, then I can still use rectangular, but it might not be going in the, the normal horizontal vertical directions. And so if I turn it like this, that's great, but then I've got to get all these forces kind of go in the right directions. And so in the end, some of that force will be going, I should draw that a little better. Notice most of that force will be going down into the hill, the normal force into the car, and then there'll be a little bit of it actually, going backwards. Yeah, doesn't that make sense? Because if I kind of take the brakes off, it's going to roll backwards, isn't it? And so that little force up there, if I actually move it so that it's all kind of emanating from that point, since vectors move. And so I can see in my picture that this angle right here must be 7 degrees. Notice it's so small that I can just kind of tell without even kind of having to think any more deeply about it than that. even though, 7 degrees is over here and that's not really connected to my triangle. So I know that's 7. So of course, if I say 19,620 times the cosine of 7, that would give me this over here, which is 19,474. And if I say 19,620 times the sine of 7, I'll get that teeny little distance across the top, which is 2391. Is my free body diagram complete? Are those all the forces that are on the car? If it was a skateboard, that would be all the forces there are on it. Well, that's actually not true either. If this was true and that was all of there was, then the car would be falling through space and backwards, right? That's the only 2 forces on it. Is it falling through space?
Like, oh, I was assuming the y coordinate or axis was normal.
So you got the normal of the ground pushing back. So that's there too. I could easily miss that. Now it would be a skateboard. Does that make sense? And so if you put a skateboard there, it's not going to sink into the dirt, but it is going to roll backwards. Is this car going to roll backwards? No, because it's got a motor, which is propelling it up the hill. And so there's a force there too. Now it's complete. Now, yes, it's got a speed and so forth, but I'm drawing the free body diagram entirely in terms of forces. And it says it's going uphill, which means that force uphill must be bigger than the 2391 going downhill, or I wouldn't be going uphill. Isn't that true? I think these problems are hard. I mean, there's just because like you were saying, Caesar, it's like you got velocity and all of a sudden there's like all these numbers in the problem I'm trying to mix in. But the reason I'm illustrating this is because I saw this on the test. It's extremely important to slow down and get like a really good free body diagram, because if you're missing anything, it just isn't going to work. So I'm a little lazy because I didn't actually draw it free. I just kind of used the picture over there, but that's cool. I have a free body diagram now. And so now I can actually start, well, solving problems. Well, this is no different than what we did before. Like, don't I have the sum of the forces in the x direction equal mass times acceleration in the x direction? And notice this is kind of cool. You'll see this in the book sometimes, but notice I'm actually defining positive x as, and I put a little arrow over there next to sigma saying it's uphill, like I'm in the direction the car is moving. Okay, so what would that mean? Well, what are my forces in x? Ah, good. Look, I got a great free body diagram. No problem. This can be easy. Force of the motor positive, force of gravity, the proportion of the 19,620 that's going downhill, that's backwards. My arrows are drawn correct. And that would be the mass of the car. Notice it's mass. That's cool. Not weight. It's not a force. So it's like I can put 2 in there, 2 megagrams. But what's the acceleration of x? Because it said constant speed. Remember how much trouble that was to figure that out sometimes, but here they said it's traveling up the hill at a constant speed. Oh, okay. Well, then there's no acceleration in x. So, oh, okay, well, force of the motor minus 23,991 equals 0. Then that means the force of the motor is equal to 2391. Now, a second ago, I said, well, wouldn't the force of the motor be bigger to go up the hill? Like if it's going to go up the hill, it's got to be bigger. But remember, force is mass times acceleration. And so if it was bigger, then it'd be accelerating. If it's not accelerating, then it's the forces are equal, which is kind of weird, isn't it? So that's entirely because it's not accelerating. And of course, you can see in this problem, if they had told us that its speed was 100, and then, oh, by the way, at the point we're at right now, it's accelerating by 50 or something like that. Well, then we could have thrown in acceleration of x is 50, and we know the mass of the car, and we still could have found the force of the motor. Does that make sense? So it's just kind of cool here that the acceleration happened to be 0. Again, I really haven't even read what it's asking. I'm just thinking of formulas that I have. I'm not smart enough to answer this question if I read what it's asking. So then I'm thinking the same thing with respect to y. And notice positive y is actually kind of in that direction. So the forces in the y are mass times acceleration in y. Do I need this? Does it make sense? I don't know. Forces in y, I've got normal of gravity going up, normal of the ground. It's not really gravity. I called it G for ground. The normal force of the ground, could have said NR for road or something like that. That's going up. And the proportion of the gravity that's in the y direction is going the opposite of that. So that's 19,474. And that also equals mass times acceleration in y. So I don't like that equation. I know mass, I can throw that in, but I don't like the fact that I've got a, y, and ng. Anybody have any thoughts on that? Think about how the car is moving in y. If I'm going up the hill, how's the car moving in y? Remember, the x-axis is the ground. Is the car moving off of the x-axis as it goes up the hill? Staying on the x-axis the whole time, which basically means the velocity in y is nothing. The acceleration in y is nothing. So again, I don't think that's obvious. That's kind of confusing, isn't it?
Ground, I mean, where you have the cosine.
Now, remember, when we were on a curve, that wasn't the same. They weren't the same when it was on a curve. And the reason was because the curve was pushing you in another direction. And so it caused more normal force. But when you're in a straight line, as long as your car's not sinking through the dirt or flying up in the air, then the normal is the same as the gravity. So that's just, again, I think that's hard. I don't think that's obvious. I think I got a reason about that, you know. We got to reason about that a little bit to get that. So great. I just got the car moving constantly up the hill. There's no prohibition. Since the force up the hill is 2391, then there could be a velocity associated with that. Because the forces are equal doesn't mean it isn't going in that direction. It just has to be going in that direction constantly. Well, let's think about what we added to this today. We said power is a force times the velocity, right? And that's what they asked. They asked about the power of this car, like what's it going to take to get that to happen? I mean, the motor's got to produce 2391 newtons of force to get it to have a constant acceleration of 0 and a constant speed. It's got to generate that. Oh, hey, I know those two things. I know the force. The force of the motor, we said, was 2391 newtons. And we were told it was traveling at 8, was it? No, 100 kilometers an hour. Yeah, and notice the units are going to be all wonky there because I need the units to be Newton meters per second in order to be able to talk about watts or, you know, whatever. I mean, that's the standard way to say it. So there wouldn't be anything wrong with this if you just said the answer is Newton kilometers an hour. That's kind of okay, but you just wouldn't be able to compare it to other people's cars, so to speak. So it's not just using the standard units. But again, do this just logically. Don't. So kilometers, let's see, I need kilometers to go away. So they got to be down here. I need hours to go away. Instead of hours, I need seconds. Instead of kilometers, I need meters. That's the algebra of fractions, right? So now I just need to go get on my phone and see how many meters are in a kilometer, how many hours are in a second. Kilometer is 1,000 meters. So 1 kilometer is 1,000 meters. I know that because of kilo. There's 60 minutes in an hour and 60 seconds in a minute. And so I guess that'd be 1 hour is 3,600 seconds. If you didn't figure that out yourself, you could jump first from hours to minutes and then from minutes to seconds. You could have 2 fractions for that. But again, this is something I can't overemphasize in terms of being good at all of these hard calculations that you make in all your different classes. So kilometers will be gone, hours will be gone, rad, Newton meters per second, cool. If I multiply that out, I get 66,422 approximately Newton meters per second or watts. Either one. You've probably heard of electrical grids as producing a certain number of kilowatts. So that's 1,000. A watt's so small. A watt's so tiny, it's almost immeasurably small. So they're almost always measured in kilowatts.
But they could be horsepower.
Yeah, in a sense. Like what's a light bulb? When you get a new light bulb, what does it say on it? What kind of numbers do you have? Watts, like 60 watts for a lamp, 60 watts. That means in 1 hour it will consume 60 watts of electricity. 1 kilowatt, 1,000 watts costs like 5 cents on your power bill. So if you had a 100-watt light bulb and you left it on for 10 hours, that would be 1,000 watts used. That's 1 kilowatt, costs 5 cents. So, if your dad's like, turn those lights off, you're born in a barn, those kind of things. That's kind of true, but it's like, here's a nickel, dad, and now we're good, right? And because that's kind of true. Now there are things that take a lot more power. If you stand in the shower for 30 minutes, that's a different deal because it takes a lot of power to heat water up. And so there's things that take power in your house and things that don't. Lights are not one of them, actually.
What about a biker or rower at the gym?
That's exactly right. Yeah,
Say how many watts you-
that's exactly right. And that's the language of this world. And yeah, I'm sitting on a rower in there and I see exactly the same thing. I sit there and pull on that and I travel 1,000 meters because that's all I have ADD or something. I can't sit there any longer than that. It's like 5 minutes and I got to go somewhere else. But yeah, I noticed that it lists watts on there. And so, again, that allows me to kind of see what did I just do? And in the end, I could convert that to, hey, I heated my house, or, I got a light bulb, man, sitting there. Now, we'd be done with this, except for they went on to say, determine the power developed by the engine if the automobile has an efficiency of 0.65. And so again, we've got this equation, epsilon, which is 0.65 equals power out divided by power in. So what did we just calculate? That's 66.
Power in. Oh, that's power out.
Yeah, notice the other problem with this is that unit is watts. And so it didn't say how to answer it. But again, the common answer to these questions is horsepower. Like nobody talks about watts in a car. So but again, is this the engine or is this the car moving up the hill?
That's the car.
This is the car moving up the hill.
That's the power out.
So that's actually the power out.
Force generated by that.
So
That goes to the-
yeah, so basically it's like, what power do you have to put into this car to get it to go up the hill in that way? Again, I don't think that's obvious. I could be talked into doing that more than one way. So if you take 66,422 and you divide by 0.65, you get a significantly larger number. And that sort of makes sense. I'm gonna have to put that many watts of electricity or energy in to the car because of the waste associated inside the engine and all of the gear systems that transfer that energy into the wheels finally to get it to actually travel up the hill in the way that we said. Now, what if you wanted to convert this to horsepower? you should think, okay, I need horsepower on top and I need watts on bottom. I don't even have to know such a thing even exists. If I want watts gone and I want horsepower to exist, that has to be the case. So then I know, oh, I got to know how to convert from horsepower to watts. I got to get online. Hey Siri, what's the conversion between horsepower and watts? I wrote it down for you a little while ago. And we said 1 horsepower was 746 watts. So wherever I get this conversion, oh, okay. Divide that by 746 watts and you get about 137. That's probably the answer you'd see in the back of the book, but it wasn't wrong before. That's why I boxed them both. Didn't say how to answer it. Does it make sense that that first answer, 102 watts, is like 102 kilowatts? It's actually 102 kilowatts, and that's kind of a little more accurate. I forgot this, but we're going to be passing by the powerhouse up there in Prospect halfway through the trip, and one of my friends works for the power company, and he told me how many kilowatts of electricity that plant produces, and he said it pays for itself like in 1 month. In 1 month's operation, it pays all of the operating expenses of it, and the other 11 months they're just, raking cash in. Yeah. So I can't remember what he told me what the kilowatt number was, but again, it's just kind of cool to hear these words and start to make sense of, what they actually mean. Yeah, I've heard gigawatt before.
Yeah, 10 to the 9.
Let's see. Okay. So a bunch of problems kind of like that. There's not too many in the book. There's one other problem like this I want to do, but we'll see if we have time. I want to switch to kind of the last section now, which is, what is it? Page 14.6. So really that was 14.4 and 14.5. 14.6 is talking about the conservation of energy. And this is on your note sheet, but it basically comes down to this. If you have a certain amount of kinetic energy at the start, which is energy of motion, and you have a certain amount of potential energy. So again, this is the skier at the top of the hill who's already going 5 miles an hour, and then he's way up in the air. So he's still got a whole bunch of distance to travel down. So he's got some kinetic energy at one point and some potential energy at another point, and then he kind of goes down the hill. As he goes down the hill, does it make sense? His kinetic energy, his speed will increase, but then he's giving up his potential energy, his height above the ground to do that. But it's conserved if there's no friction loss, or at least if you can neglect it because it's so tiny. So you're going to have the same energy collectively, energy at A, energy at B. We said yesterday this was the 1/2, or Tuesday, this is the 1/2 mv squared part. That's the energy measured in mass times velocity. And potential energy was work. It was a force times the distance. And we saw that those were the same exact unit. We said those were equal. Those are both measurements of energy. So you have potential energy, kinetic energy, certain amount at the start. And if you don't lose anything from friction, wind resistance, that kind of stuff, or at least if we say that's negligible, then it'll still be the same. It'll be conserved later on. That's kind of cool. And keep in mind, like, what does this have to do with what we just did? Because it kind of feels like, why are we doing this now? Like we just stopped and did power in the middle and then we're suddenly back to what we did the other day. The answer to that's kind of yes. And there's part of me that says, maybe I should teach these in a different order. Like this is the order the book had them in. But remember what we learned today is power is just, well, energy here. It's just energy over time. It's still energy. It's just energy over time. Having said that, I guess I would say I disagree with the author on that a little bit. So I will add here, just as a kind of a note, this has to be frictionless for it to be this simple. Could you subtract a little bit of energy out of that system?
Yes.
You know, for friction? Yeah, you absolutely could. If it was possible to do this, that would solve our energy problem. Do you understand that? But we do lose because of friction, and so it isn't kind of perfect. But this has to be frictionless in order for this to be the case. So let's take a look at this problem, which you have in front of you. So first of all, without reading anything, just stare at it. So here's this dude and his roller coaster. This is one of those classic old roller coasters where you're literally just coasting. So right now, whatever height that roller coaster is at, it has a lot of potential energy because it's way up in the air. Force of gravity is pulling down on it. It wants to go down. If it was already moving from before, then it might even have some kinetic energy, some speed related energy, but it could just be sitting there. And then this is where, you know, somebody gives it a push and then it goes down the hill. So it might not have any kinetic energy. It might not have any velocity. So we don't really know yet. We haven't read the problem. But of course, when it goes down, it's going to lose, by the time it gets kind of down here on the bottom, it's going to lose all of its potential energy, its force times distance, and it's going to change that to velocity. So it's basically going to be on the ground, but on ass now, right? But then it goes up in this loop-de-loop thing where it starts to give up that speed and it gains elevation. Now, what would be bad is if it didn't make it to the top and then just fell, right? Which is what it would do in the old-fashioned version of these. Now they kind of hook onto the rails and they sometimes have even kind of power associated with them. But if this is purely gravity, that will work. You could coast down on a skateboard and actually pull that off as long as you can kind of handle the G forces. Remember, this is a curve and it's causing you to change directions. You might crash as you're upside down just from disorientation and the sheer G forces you might not be, and that's upside down. Like remember, your legs would collapse upwards because of the amount of force of the, you know, of it saying, no, you're gonna go this way, right? So you could actually just fold up there at the top of that if you started from too high. But theoretically, this could work. Does that make sense? Entirely with a skateboard. If you just pushed a skateboard down it, it could actually do that. Did y'all have good childhoods? Hot Wheels? Hot Wheels?
So G-force is acceleration.
What's that?
G-force is an acceleration.
Yeah, that's exactly right. I mean, it's basically gravity. It's G-force is gravity. So it's basically gravity pushing. And that's why I mentioned it here, because it's actually upside down. Isn't that weird when you're right at the top of that? So the point is collectively, if there's no friction loss, I'm sure they said that in there. Is there some place in here where they said that? Yeah, right here. Neglect friction.
Yeah.
Okay, cool. So then energy is going to be conserved. So let's see if we can figure this thing out. So this is kind of a good problem because here, notice they didn't tell us how high we are. They said H, almost like, well, you're the engineer, designed the dumb thing. Like how high should you start in order to be successful in that loop-de-loop? Notice there's two of them. And so there is a chance you could actually have enough energy to make it around the B one, but then you get over to C and then you don't make it. Or it could be the other way around. Like if you had made it through B, then you would have made it through C, no problem. So this is kind of an interesting one because there's sort of two places we got to make it. And so they're saying, hey, design this thing. How high up there do you need to be in order to make this kind of fly? Well, let's just dive in relative to this formula that we've been looking at. So Let's just try this from A to B. So basically what we said is 1/2 mv squared potential, I'm sorry, kinetic energy plus force times distance where I am at A will be equal to the same exact thing when I'm at B. Now, how do I distinguish that? Well, I guess I could say this is the velocity at A and this is the velocity at B. I could say this is the distance is like the height at A and this is the height at B or something like that. Maybe I could say it like that. I don't know. Okay. Well, I do have my mass. I'm told the mass of the car is 700 kilograms. It's not asking for force, just mass, 700 kilograms. Great. Let's see, it starts from the top of the hill with a speed of 3 meters per second. And so this already did have a speed. And you should appreciate if this is a real roller coaster, it would have to. Because if it got up there and just stopped, does it make sense it could roll backwards? Like it can't have that happen. Like they've got to have enough speed to make it over the top. And obviously different people in the car, there's a little bit of rain on the track. Like you could mess with the friction of this whole thing and they won't make it. So it makes sense that it would have a velocity there. Again, when I write what I just wrote here, I have a tendency to forget the little squared up there. It's like, oh, 3, but it's squared. It's actually 9, right? So I know that. What's the force up there? How do I figure that out? Force is mass times acceleration. Acceleration of gravity is 9.81. I'll be lazy and leave the units off. So that's going to be newtons now, right? Force is mass times acceleration. So that's my force. And then my distance up there, like how high I am above the ground. I mean, there's no reason to rename this in one sense, but I guess I'll just call it H since that's what it said in the figure. But it's like, I don't know that. So, that's not good. There's something I don't know. So what about over at B? So now I move to B. So as I said, I'm working from A to B. So my mass hasn't changed. Maybe somebody blew chunks and there's a little less mass by then. I don't know what velocity of B is. Force hasn't changed. And I do know the distance at B because they told me it's 15 meters, right? Do I like this equation?
Yeah.
I don't like it because it's got 2 unknowns. It's got H and it's got velocity of B. So I don't really like this equation too much. I can't figure anything out about this. That's kind of stinks. So, my first thought is like, is there some other equation I could come up with? Notice they said though, determine the minimum height of the hill crest so that the car travels around the inside loops without leaving the track. What does that mean?
Something cancel out.
Does it make sense if I did know how high I was? Like if I had a height, if I just said, for the fun of it, if I just said, okay, let's just make H 25 meters, then I could actually know the velocity over there. And what would happen if I got to B and my velocity was 0? Yeah, that's not good, right? Because I mean, if the velocity was 0, then you might, and this would only be if it was stuck to the track, like mechanically, then you might actually roll backwards or forwards, like you're right at the edge. And so that's not so good, right? So that's maybe not so good. If it was literally like Hot Wheels, then you would just fall straight down, everybody dies, right?
If it's conjugate, doesn't have the long conservation of energy, would that mean that in your ending position, you have ending position where he's on the ground, would he still have the same velocity you initially started?
Yeah, if there's no friction loss, then this energy gets conserved and he would get all of his speed back again. Like whatever speed he had right here, and he goes up here and he's losing, and then gaining, and then he gets back to the bottom, and then he's got all of his speed back again, same exact speed he had before, which again isn't realistic because there would be a little bit of loss. Maybe it's negligible, and so we don't have to worry about it. Maybe it's not negligible, and if we don't worry about it, bad things happen. But just as a side note, it's just interesting. H is not 25, but if it was, the velocity of B here would be 14.32. So that kind of feels like, oh, okay, that'd be good height then. I mean, I still got some speed up there, right? So I'm still going pretty fast. So, you know, again, you could say maybe that's too fast. I don't have to think about it, but the point is if H was 25, then I'd be able to solve this because I had one. And so, you know, I could kind of guess and check here a little bit. Let's think about something else. What's going on up here at B?
When you have your weight pointing straight down, you have I'm guessing the tracks holding you up, so that will be pointing up.
So remember that whole business when you're traveling on a curve, we're traveling on a curve here. So part of me wants to say the minimum would be if the velocity had been 0. And so notice my velocity was 14. And so I'm thinking, oh, 25 is plenty high enough. We're great. This is awesome. No problem at all. But is that really true? Let's just think about this for a second. So we're traveling on a curve here. So is that, since we're traveling on a curve, not on a straight line, do we have to kind of think about this? I'm not really sure. Let's just kind of reason about it a little bit. So what forces are on us? Well, right at the top of B, does it make sense that you have gravity right there? So this is a very unique spot. It's straight there, not at an angle. So that means that 700 times 9.81, I'll write it up here. That's, I wrote it down somewhere, 60, 68, 67. So in my free body diagram, what's going on up there? Well, I have gravity pulling me down. Does it also make sense that you have a normal force of the track pushing down there too? Do you notice what direction I drew that? So right now, do you agree the floor is pushing up on me? And that's good because I'm not falling. But if I was to stand on the roof, I'm just going to fall, right? Well, unless I rip around this way so that I'm actually getting shoved into the ceiling, in which case the ceiling's going to have to shove back, right? So that arrow is actually going the right direction. That's the normal force of the track. And we need that to not be negative. We need, if it's negative, you are falling. You did not have enough. We need that N of T to be positive.
So then your AN has to be big enough to surpass that NT.
That's exactly right. So you actually have 68, 67. Is this a positive or negative number?
Positive is the direction of the radius.
It's aiming toward the center of the circle. So it's actually positive, even though it's down. Again, that's troubling, right? That's why I bring it up again. And NT is also going down. So that's the two forces that are actually pushing on you, and they're both pushing you in the positive direction. And that needs to be equal to the mass, which is 700, times the acceleration normal, which I think I'll just replace it with this v squared over rho.
But we do have rho.
But we do have rho. This is a loop. They didn't draw it perfectly here, so I think this is a little deceptive, but that's actually a circle. So since its diameter is 15, then its radius is 7.5. In the problem, they called it a loop, but in the drawing, that actually doesn't look perfectly circular. So I think that's kind of that's a tricky problem.
Well, at the end it says take row B equals 7.5, so I think they're.
Oh, there we go.
Right. at-
Yeah, I didn't see that. You're exactly right. At the very end, they said take row to be 7.5 meters. And so, okay, I guess they are telling us that. Again, if that wasn't perfectly circular, could that still be close enough? I would say it probably could be. If this is a roller coaster, I'd probably build a factor of safety into all of this stuff. And so it's like, it's pretty close to a circle. That's not, I mean, there's no equation, right? Remember we had to have an equation for that weird shape to get all this to work. So it's like, there's not really an equation. So that's kind of interesting. So notice I'm not super happy with that equation either, because it's also got two unknowns. And so that's true, but not super helpful. But let's think a little bit more about what this N of T number is right here, that normal force right there. Notice they said, what's the minimum height? Yeah, if you're going really fast around that, does it make sense there'd be a ton of normal force pushing on you to change your direction? But if you barely made it, there wouldn't be any at all. Like a very minimum would be when N is T of 0. That'd be right on the edge. And of course, if we figured that out and we found the minimum height to be at, we'd of course say, well, let's make it a little higher, right? We'd have a factor of safety in, but it's kind of cool to figure out the, like, if you any less than this, and everybody dies. And so we found the line, and then we'll, add 20% or whatever it is you choose to add. But this would actually equal 0 at the minimum. And so oddly, in our last problem, in our previous problem, we said, oh man, there's two unknowns. There's a height and a velocity. Well, thanks to this equation, we can actually determine what that velocity would be. And oddly, it is not velocity at 0. That's the thing that's really weird. I would have thought the velocity there would be 0, but it's not going to be. I want you to think about why that is. So if you solve that equation with N of T being equal to 0, you get the velocity at B is 8.58.
Because it's fighting the acceleration and the tangent.
Yeah, it's because it's fighting gravity. In other words, it takes that much speed to fight gravity. Any less than that, and it won't win. So that's basically taking care of the gravity that's pulling down on you. Does that make sense? That's why the velocity is not 0, even though my instinct was it would be 0. So we actually do know the minimum velocity at B. Notice what I said earlier. We got, when I just made up 25 and said, my gut reaction was I made up 25 for the height, and I had 14 meters a second, and I thought, oh, that'll be great. But notice, if I had gotten unlucky and that had been something like 6, I would have thought the same thing, like, oh, that'll be great. And then everybody dies. So it turns out the minimum velocity is actually 8.58. In other words, the normal force being 0 is what I had to set to 0 here, not the velocity. Isn't that kind of surprising? I mean, I find this to be hard. I don't know about you, but. Okay, well, if that's true, then I can take this velocity and put it in back here, and I can actually solve for the height.
It's kind of hard to understand how that velocity is.
It's the velocity and the direction. It's fighting gravity.
Yeah, so the interesting thing about conservation of energy is velocity is a certain amount of energy, no matter what way it's directed. So when you're using velocity as an energy measurement, it kind of doesn't matter what direction it's going. Now, it does matter if you care about where you're going, but in terms of energy, it's just a measurement of energy, so it doesn't matter what direction it's going. So predictably, notice we got a number significantly less than 18 or less than 25 earlier when I just kind of said, oh, what happens if it's 25? We got a number that's less than that. So notice that's the minimum. Now, the interesting thing is is that enough? Because we're not done. Is that enough to get us past C? What if C was the place where everybody dies? Like, you know what I'm saying?
So then do we make our B our initial point now and C our final? Or B?
Yeah, I mean, so now you could just say, oh, okay, you're at B with a certain speed. Or you could actually go clear back to the start and say, well, you're at H and we now know that's 18'3" and we can see what happens down there at C. Any of those work. I think I'll take that approach in the interest of time. Like, let's just go straight from A to C now. Now that we are saying H is 18.3. Or yeah, like you said, you could go from B to C as well. That's totally fine. Does it make sense that you're going to be going faster at C than you were at B before we even calculate this? Because you're lower. So you've given up some height, therefore you got some more speed since energy is conserved. You gave up potential energy, you dropped down 5 meters. So you're going to be going faster. So part of me wants to say, oh yeah, we'll be good then. We don't need to calculate this. The other part says, wait, speed wasn't the whole thing. It was that normal. If that normal is 0, that was where everybody dies. So I could go from B to C. Actually, I think maybe we will. That'll probably feel better to you as we do this. Let's go from B to C. Okay, quickly. So 1/2 mass times velocity squared at B plus our potential energy at B is going to equal the same exact thing when we're over there at C. I notice I know more stuff than I knew last time, so this actually is going to go a little bit quicker. My mass was 700. That was terrible. We just got done saying our velocity was 8.58. Force of gravity hasn't changed. I turned that into a number a while ago and it was 68, 67. And we are 15 meters above the ground there. Again, this is defining the ground as 0. So I know everything on that side. I know exactly how much energy I have over there. That's cool. Do I know what's going on the other side? Well, my mass hasn't changed. I don't know my velocity, but the force of gravity hasn't changed. And my distance I know is 10. So, hey, I like that equation. It's just got velocity at C. Sweet. So if you punch that in, you get a velocity at C of 13.1. Now, again, all by that self, despite what we learned a second ago, is that actually isn't enough to know whether we died or not. So I kind of have to come up with that normal calculation again. Is that normal calculation more than 0? I need it to be positive. I need the track to be pushing against me in order to make it around there. So we found the minimum for the first one, but I wonder if it worked for the second one. And so like before, the normal of the track plus 68, 67 has to equal mass times acceleration. And since acceleration is v squared over rho, in this case, rho is 5. I know every part of that equation too. Are you okay with that? It's a little fast. I feel like it's kind of hard. Like you definitely need to go back and study this again. I'm basically just quickly plugging in what we did right here, just redoing it. Except for now we have a different speed. Do you understand that we are hoping that n of t is positive here? If it is, then that's good. If it's negative, that means, oh, they made it through B, but then they died at C. So then we'll have to go back and get higher so they don't die at C. Does that make sense? So can you tell by, well, actually, that's not true. I was going to say, can you tell by looking, but you can't. If I take 700 times 13.1 squared and I divide that by 5, I get a number bigger than 6,800. Good deal. I get that N of T is 24 newtons. It's positive, so the track is actually pushing really hard right there. Oh, I never did that. Sorry. $17,158. That's quite a bit of force. So it turned out we got lucky effectively. They barely made it through that first loop because we didn't start much higher, but then they had enough energy to kind of totally easily make it through the other one, no problem. Which actually kind of makes sense because the other one's lower, right? It's lower.
It has a changed direction of the acceleration fast.
But yeah, because we're dividing by 5 instead of 7.5. So in the end, this is sort of the big answer. It's like, oh, cool. If we put them up there at 18.3, they'll be great. So let's add a 50% factor of safety and we'll put them up there. What is that, 27? Let's put them up, let's put it at 27, just so we have plenty. But then we're still going to have some stunt doubles to test it and make sure the G forces don't thrash them, right? So
they might make it a little bit higher.
yeah.
For safety factor.
But notice that second one has a lot of that normal force, which is effectively changing directions. That's really big. That feels like large. Again, I don't really have I'm not good at newtons, but if I turned it to pounds, then I would have a sense of like, oh man, that's going to be brutal. That's a hard problem, and that's a lot to think about right there. I think that's a really interesting question. Okay, I need to shut up. I may do a little more with this